So I'm here to talk about like Iceberg, some history, the internals and production challenges when you run Iceberg in production. And finally, I will be talking about TableFlow, which is a new product from Confluent to solve a lot of these problems and make it easy to use Iceberg in production. So this is a picture of like a famous book called Start With Why from Simon Sinek. Like, has anybody read this before? Great, there are few folks. For others, like it's a great book, give it a read. So the book talks about like why you should always start with why. Like if you're a leader, like if you're a founder, you should start with your why than going into what and how. So apart from that aspect, I found starting with why very important when you are learning a new technology. Like why the technology was created, what pain points the creators was facing before, and things like that. So with that, it's good to understand, like go through a bit of history to understand why Iceberg was created in the first place. In the last decade, Hadoop was widely used. Hadoop is a distributed processing framework, and Hadoop distributed file system, which was the storage powering all this, was used widely. A lot of companies was using it, and Hive was like a data warehouse infrastructure built on top of Hadoop distributed file system. So people wanted to run analytical queries, simply put like some SQL queries on Hive, like the data on your HDFS. So in Hive, a table is nothing but a data file within a directory. If you need partition, you create subfolders and you put the data in there. So it was like as simple as that. In early days, it scaled well with the big data at that point, but it has like numerous limitations like schema evolution. For example, in Hive world, like there is no way to rename a column. So if you need a rename a column, the closest thing you can do is like drop a column and add a new column, but it's not same as rename, because when you rename with the new column name, you should be able to read the old values as well. But in Hive, that was not possible, and there was like other schema evolution issues as well. Second was reliability. In Hive, there is like no concept of transactions or like atomic commits. So if you, let's say, want to add a file and remove a file, so it's not like an atomic transaction. So you could see dirty reads, like partial reads and stuff like that. And another problem was that because of like there is no snapshot isolation and stuff, a writer can overwrite the writes from a previous writer. So things problems like was there. Third was like the main important problem, the performance. So Hive didn't have a good metadata layer, which means Hive relies on file listing in a directory to identify which files are part of the table. And it's pretty problematic when you go to a large scale. And another pain point was like static partitioning. So like I said, a table is just a directory with files in it, and if you want to partition, you create subdirectories. So as you go through, like let's say your query pattern changes, you want to repartition it, the only way for you to is like rewrite everything, which was like very costly if you have large scale data. Netflix was using Hive in production, and as we all know, Netflix has one of the best recommendation system in the world, and they have a lot of data to make it work. So at their scale, they hit a lot of limitations of Hive, and in 2017, if I remember correctly, they came up with Iceberg, which was created to like takes care of a lot of limitations they were facing with Hive. Like one of the main problem they were trying to solve is like having ACID properties, more like your database, your data lake should also have ACID properties, so that problems of dirty reads, the lack of snapshotization, all are taken care. And apart from that, they wanted to have good schema evolution, like the schema evolution you see in like databases, like add columns, remove columns, rename columns without losing the old data. Another problem with Hive was like it was mainly created for batch workload, but if you have like streaming, it doesn't have to be real time, but even like you are making data available in your lakehouse, let's say every minute or two, Hive struggled a lot. So Iceberg was like in a way created to take care of that as well. So as a result, like Apache Iceberg was born, and it's an open table format that designed at Netflix and later donated to the Apache Foundation. A table format, like to define, if you define the word, it's nothing. It's some rules and some metadata to organize and manage data files so that it looks like a table for the external user where they can query. It's as simple as that. Then it solves the limitations of like Hive, and the key features if you look at for Apache Iceberg is, one is schema evolution without breaking the old data. Second one is time travel, because you have snapshots. A snapshot is nothing but like a point in time view of your table. Let's say you have like a snapshot S1 with 100 records, you add 3 more records, you have a snapshot 2 with 103 records. Now it's up to you whether you want to read based on snapshot 1 or snapshot 2. So you get that time travel feature in Iceberg. Another one is like ACID transactions. So the new data you added becomes available as like an atomic commit, and there is no problem of dirty reads and stuff. Another, with this new design, batch and streaming was well supported. Then another feature or improvement that Iceberg has, and it is like one of the most important features in Iceberg, is column statistics. So for each column you kind of stores some statistics about it in your metadata. So for example, the min and max stats, how it's helpful is that, let's say you are running a query to find like all the people aged between 40 and 60. So if you have column statistics and a data file has like a, for this age column, the min is 20 and max is 30, which means there is no records in that data file which satisfy the query you are running. So you don't even need to look into that data file, thus optimizing your query performance. And another good feature that Iceberg has is like hidden partitioning. So in case of Hive, if you, let's say you have a date column and you want to partition based on week, the only way to do is that you add a new column that has this like transformed week data. But in case of Iceberg, you don't have to do that. You can have like a partition spec defined based on the date column, and you have like transform functions like week, year and stuff to use that. And another thing that Iceberg provides is partition evolution. So let's say you partition by some column, and later if you want to change that, let's say your query pattern has changed, you are free to do that. And Iceberg takes care of, let's say when you run the new query, to read from these both partitioning schemes, and you can have like some background job, async job, to rewrite the old partition scheme data. So yeah, now we have seen why Iceberg was born and what are the core features. So now it's good to go a bit deep to understand how exactly like how Iceberg takes care of it, like how the table format actually works under the hood. So this is a picture, like our diagram I copied from the official Apache Iceberg website. So like if you want to understand the metadata structure or like overall how Iceberg works as a table format, this is a single picture you need to understand. So if you understand this, like you kind of understand how Iceberg works. So there are 3 layers mainly in the table format spec. First one is like the catalog layer. Catalog is a mandatory thing for Iceberg to work. Then there is a metadata layer, then there is a data layer. So we can start from the bottom. So in the data layer you have data files. So these are the files that contains your actual rows in the table. So typically this will be like a Parquet file, which is a great columnar file format, but Iceberg provides ORC and Avro as well. So each of these data files, like if you see go to the next level, there is a manifest file. Manifest file has a list of data file it points to, and for each data file it stores the column stat as well, like min max, the row count, null count, and stuff like that. So that's the manifest file. The next layer or next level is the manifest list. As the name suggests, it is a list of manifest. So if you see this manifest list, it has like two entries. The pointers are like entries in this list. So that's manifest list, and a manifest list has a one-on-one correspondence with a snapshot. So if you see there is a snapshot S0, so this is the manifest list that represents that snapshot. Same way, if you go there, the snapshot 1 has like a corresponding manifest list. So that's about manifest list. And when you go one layer above, this is we call like metadata JSON or root metadata file. This is the first file that the query engines need to get to find the Iceberg metadata. So if you look at this metadata file, there are like two snapshots, S0 and S1, and that's what gives like the snapshot isolation and time travel queries. So I will talk about how query planning works in a bit. So the last layer is the Iceberg catalog. Iceberg catalog is nothing that's has like the details of the table and what is the current metadata file. That all it has, and it should support like atomic swap of like the metadata pointer. So you can build catalog on top of any like database. For example, there is like a Dynamo catalog, and in our case, like in TableFlow, we have like an internal key value store. On top of that, we built a catalog. So that's the overall structure of how the table format is defined. And if you look at how a query will be run, let's say when you run like select star from db1 table1 where age is between 40 and 60, what happens is that query engine will first make a call to the Iceberg catalog asking that, hey, I want to run a query on this table, what is the current metadata file path? So the Iceberg catalog will return the metadata file path to the query engine, the latest one. At any point there will be only one metadata pointer, like the current metadata file. So the query engine will go ahead and download that file, the metadata file you are seeing. So it will see that there are two snapshots, S0 and S1. Given that customer, like the user haven't specified any specific snapshot, it will go ahead and start reading from the snapshot 1, which is the latest snapshot. So it will just download the latest manifest list for that snapshot. And even at this manifest list level, you will have aggregated column stat, like aggregated min and max. So if the manifest list says that, okay, there is no data file within your range, then we can stop the query there. You don't need to even go further. For let's say there are like some files, let's say these data files has some data that satisfy our query. So from the manifest list, we will get the list of manifest, and it will prune at that level as well. And let's say only this manifest file has some data with the query we are running for. So it doesn't need to go to this subtree or this subtree. It just have to get this manifest file. It will get that. It will again check if there is any data file, like which are the data files which satisfy. Let's say two of these data files has the records which satisfy our query. Then now the query engine only needs to download those two data files. So that's how column stats helps to prune, and you don't have like, instead of 9 data files, you just have to read 2 data files. So that's how like the overall structure and the query optimization works. Now, so we understood like the internals and how all these good features are implemented, and it sounds like Iceberg is like a no-brainer. You just adopt it in production. But when you get into running this in production, especially let's say you have a good scale, so if you have like a 500 GB, just run Postgres, don't even think about Iceberg at this point. So but if you have good scale, you will hit multiple issues. Some of this is covered in the first talk as well, so there will be some overlap. So the first one is like the metadata growth. So if you see this tree again, so how the snapshot 1 was created, it's based on the snapshot 0 plus the extra data files you added. So these two manifest was present here. So the third manifest was added with the new data files. So that's S1. So you keep adding this manifest. So the metadata manifest like count you need to get keep increasing. Let's say there are like 1000 manifest file you need to get, and in S3 because of like the IO overhead you need like giving a ballpark like 100 ms to make the initial connection. For 1000 manifest file that's like 100 seconds just to initial connection for the manifest file. So if query planning is going to be take that long, I don't know if we will wait for the query to finish. We might think that yes, things are stuck, just rerun. So it's very important that we take care of this problem, otherwise your query planning is going to be pretty slow. Another problem is like the problem of small file. It was covered in the first talk. So to just a recap, so if you let's say keep producing data every minute, you will have a lot of small data files. So again the IOPS issue we talked about coming here as well. Plus the additional problem is that for each data file you need an entry in the manifest file. So all these small data file is contributing to have large metadata as well. So large metadata means your query planning is going to struggle again. So to take care of both these problems, typically we do compaction. It needs to be done on the data files, and you need to compact the manifest as well. So it's not in the hot path. So typically you need to configure some background jobs to do it, and if you are not tuning it correctly, it can be a costly operation. Another problem is of like concurrent writes. So we said that each snapshot is built on top of the previous. So if two writers are trying to add two distinct data, only one will succeed. The other one has to retry. And when it retries, it needs to create a new manifest file, new manifest list, new metadata file. It has to redo all these things. So that's the problem when you have like multiple readers, and Iceberg use optimistic concurrency control. So retry is the only option. Another problem you have like this snapshots you have, it's pretty good. You get asset properties, you get time travel, but the problem is that this can grow unboundedly. So you need to expire this snapshot so that your metadata size is kept in size. Plus when you compact files, you are replacing old file with new files. But if you have like some snapshot pointing to the old file, you can't delete those data files. It's just occupying storage space. So it's important that you periodically expire old snapshots. So if you need to do that, like it's like a maintenance operation again. You need to set up some background jobs. Another problem is orphan file. All these OCCs and retries going to create a lot of orphan files in your storage, and that's going to add to your storage bills. Another problem is like all the operational complexity. If you have to do all this, means like you need to set up compaction, you need to monitor like how is the storage cost is going, and you need to tune it. So all these things you need to do. Plus there is like a mandatory component of catalog. You need to set up that as well. Another problem is that even though we talk that Iceberg has pretty good schema evaluation capabilities, there is no central authority to manage or validate schemas. A writer can do some schema evaluation, and next day you realize that some downstream query is failing. So that's like another problem when you run this in production. So if you think about all these problems, do you even care about it? If there is a table format which doesn't have all these problems, people are just going to adopt it. Unluckily, like we don't have like a table format without these kind of problems, but we have products that takes care of this for you. So all you have to worry about is like, hey, how am I going to ingest data into my data lake? And once I do that, all I care is like querying and making some business insights and making more money based on that. So that's exactly what TableFlow, which is a new product from Confluent, is trying to solve. And It's based on the Kafka Iceberg paradigm that was initially coined by Confluent itself, and it's first of its kind. Now you have few more players in the market which does something similar, but TableFlow is still the most matured and most feature rich product you have with respect to this. So the idea is that almost all the companies use Kafka in production, and it's not a new technology. There are like lot of integrations, and for example, like you want to ingest from Postgres to Kafka, you have a connector. We have like 100 plus managed connectors in Confluent. So getting data into Confluent is like, or not just Confluent, Kafka is like an already solved problem. You don't need to reinvent the wheel. So the idea is that with schema, in schema registry and the data in Kafka, you just produce the data to Kafka. Rest of everything from materializing into Parquet, all this metadata creation, table maintenance, and everything is taken care of by TableFlow. Not just that, once you do this, your tables will start appearing in your catalogs as well. So TableFlow takes care of all this, and this is like a summary of how your life will be with TableFlow. So all you care about, like you have to do is like set up your schemas, start pushing into Kafka, and with click of few buttons you will have TableFlow enabled, and you will have your catalog syncs enabled. So all this is taken care by TableFlow. Type mapping and conversion, taking your Kafka data and using the schema you provided in schema registry, we create the Parquet files. So we takes care of schematization of data, schema evolution, and there is like support for CDC materialization. And automatically, once you configure your catalog in Confluent Cloud, you will get this data in like these tables automatically in your catalog syncs as well, where you can just go and like explore and run your queries. And the most painful part of like running Iceberg in production is the table maintenance, like compaction, snapshot expiration, orphan file cleanup. All this is taken care by TableFlow. You don't need to do anything. Or the one thing to do is like we do snapshot expiration based on the age of the snapshot. So customer can configure how old snapshot you want to keep. You can say that I only want snapshots of 1 week. So we will expire all the snapshots older than that. Another problem we talked about is like when you have multiple writers, the one writer wins, the other one has to retry everything. So that's like a lot of wasted effort and compute. So in TableFlow, you don't have this problem because we have like a single writer using a patented protocol like called committer protocol. So we use that so that like at any point of time, you have a single writer writing to the table. How do we do is that like in Kafka, you have multiple partitions. You create Parquet files for this and you submit, let's say 100 commit tasks. So instead of committing one by one into the Iceberg table, what we do is like we club it together and commit it as a single like snapshot. So that's how things are taken care. And once we do that, we have like the catalog sync support as well. There is a TableFlow Iceberg REST catalog that we built, and there is AWS Glue, Apache Polaris that support work as like Iceberg catalogs. Then there is Unity catalog, which is for Delta Lake, so which is like another table format. Then if you see the picture, there is only 2 points where as a user you need to worry about. One is like how you ingest the data. It's through Kafka. It's already a solved problem. Then your data is flowing automatically to your warehouse or your query engine. Where you go, it's there in your catalog, run your queries, get your result, and make insights out of it. So that's how TableFlow solves all these problems, so that running Iceberg or Delta Lake in production is no longer a pain. It's like an easy thing to do. So yeah, with that, it's end of the presentation. So if you have any questions or doubts, let me know.
Hi. One quick question. Are you only supporting append or you can do the upsert or the target?
Yeah, good question. So currently in GA, we have append only. So upsert is like engineering wise, it's done. We will be launching this month or next month in current. So yeah, it's like a month away from production.
Also, one more question, like when working with the table formats like Iceberg or Delta, one issue I saw compared to working with any MPP like Redshift or Synapse or Snowflake is like since there is no caching layer, data is not in STD. Always the when I query the data, if it is not on the index column or partition, it will be much slower compared to like Redshift or Snowflake and all. Is there a like are you is there a way you are solving that?
Yeah, so if you look at this picture, TableFlow doesn't come into queries at all. But there is one component here, which is Flink. So we have optimized Flink in a way that, so if you run a query currently, like let's say usual Apache Flink, it needs to go through the, let's say, the stream. So what we have done is like the stream is divided into two. The first part where we are already materialized into Parquet. The second part is like the new data which is not yet there. So if you run queries in like Confluent Cloud Flink, it utilizes both. So you use the Parquet for the old one, and for the new one you get it from Kafka. So you have like sub-second latency on your queries. So apart from that, the caching and stuff will be typically done at that side, the query engine side. For example, like in Databricks, they have like extensive indexing, not just indexing, extensive caching added so that your queries will be faster. And as far as I know, for Iceberg, Dremio also have like good implementation of the caching stuff. And the good thing is like Iceberg is just a spec, so anybody can implement the way they want, like just that they have to satisfy this thing, they can add any additional thing they want. So Dremio for Iceberg and Databricks for Delta, I've seen having this caching and like better performance.
How do you handle the small file problems in case of Kafka? Because a lot of events coming in, smaller files, let's say KB size files. How do you handle that?
Yeah, so we have to do compaction for sure, but the good thing is that if you have like enough throughput, let's say good throughput, typically the small file problem is like kind of taken care. Let's say you are pushing a lot of data and you are materializing, let's say every 2 minutes or 5 minutes, and you have enough data, it's already taken care, you have a bigger file. For smaller files, two things we do is like, one, we partition, like from each partition we club that data together into a single Parquet, so you have the chance of getting a larger file is high. So if we can't solve the problem even with that, then we have like automatic compaction running, like it's a bin pack algorithm. We look at the number of small files in your tables, and based on the configuration, like based on like the threshold, like when it's really going to affect your queries, we do the compaction and replace with like larger files. So we do compaction.
Okay. Also, the second question is, so let's say you have created a consumer group for the ingestion from the Kafka, right? What happens if there is some delay and then repartition occurs of the consumers, the readers in the consumer group? Do you read it from the beginning? How do you save the offsets? Something like that.
So yeah, when your data is in Kafka, we read it in two ways. So if your data is already tiered to object storage, so in Confluent Cloud, any topic is tiered to object storage. So if it's tiered to object storage, we directly get that from object storage. We don't go through the broker, because broker CPU is very precious. And plus, when you do go through broker, there is like maybe a cross-AZ network call you need to make. And that's like the cross-AZ network call is the highest segment you see in your bill. So with direct reads, you don't have that problem. You get directly from S3. Only for the new data, which is not yet tiered in S3, we go through the broker. And currently, the configuration we have is that we materialize within 15 minutes. So we haven't given like a sub-minute materialization. So with our current customers, it just works. And if you really need like real time analytics, you have Flink, which utilizes the same data. So it's in a way that's taken care, like even let's say our consumer that we are consuming from the thing is not there, but the data will be in tiered, we can get it from there. Yeah, thank you.
Have you guys tried the Apache Hoodie? That's also an equivalent of what Iceberg offers.
Yeah.
How's the industry experience with Hoodie versus Iceberg?
Yeah, it's like Hoodie, Iceberg, and Delta Lake. Usually, when you talk about open table format, it's like a holy trinity. But the thing is that like we didn't have like a lot of customer interest for Hoodie, so it's mainly Iceberg and Delta. So Hoodie is not currently supported in TableFlow because there is like not enough demand to spend like engineering effort on that. So it's not supported. Only these two formats are supported right now.
Basically, you were interested more with your TableFlow and TableFlow integrated with Iceberg, and then you went with Iceberg.
Yeah, so the underlying data file is same for both. The only difference in these table formats is like how your metadata layer is. So all the data file compaction, everything is like upstream, you take care of it, and you just manipulate the metadata in like Iceberg and Delta. If you have Hoodie, it's just another metadata layer you have to worry about. So we haven't implemented that because there is not enough like customer requirement. So, and another thing to add in case of TableFlow, so for a topic you can enable just Iceberg or just Delta or both. It doesn't cost you any more money. It's up to you. Like we see a topic as like equal to a table. It doesn't matter how many table formats you enable. It's up to you. If you just want Iceberg, you can choose that. Or if you want both Iceberg and Delta available, like in your, let's say in your Unity catalog, you want a Delta table. In your Apache Polaris, you want an Iceberg table. You can just select that and it just works without any additional cost.
TableFlow is a new thing and I liked it. Now, assume that I have to read say I have hundreds of Postgres tables. And the data that goes to the Postgres table are in a different frequency, throughput and all that. How do you configure your TableFlow to, is it a polling mechanism where it goes and gets the data say every 2 seconds and all that?
No, so yeah, in case of TableFlow, currently Kafka is the only way to get that data into it. So let's say you have Postgres and like a lot of tables, you have like very matured connectors to get this data from, let's say, your Postgres database to Kafka. It's like even like we have 100 plus managed services to do that in Confluent Cloud, managed connectors. So once you get the data to Kafka, the flow is same for TableFlow. So we are not trying to like, let's say, query data directly from Postgres and all, because for us it's already solved problem. Like getting data into Kafka, it's very easy. It's, you have all the tools, it's pretty taken care. So we take care of from here once the data is in Kafka.
One question on TableFlow, does it require schema registry?
Yeah, it requires schema registry, so it's already there in like Confluent Cloud. Just that you need to yeah.
What I want to understand is TableFlow open source or is
No,
it clubbed with Confluent complete product?
Yeah, it's currently like Confluent Cloud only feature.
So you had mentioned that in Iceberg there is a problem where the queries get stuck, and because the catalog is somewhat out of sync or maybe the snapshots are not well aligned, so then do you get a feedback from the query side into TableFlow to tell that that query was stuck, so you need to optimize that metadata or
No, so
snapshot?
yeah, so the queries doesn't actually get stuck. It's just that it takes a lot of time, so it might feel like stuck for the user. So you can, like when you, for example, you are running Spark, there is a way to enable debugging mode, so you get the logs what exactly happening. So there is way to get to that. So the problem TableFlow is trying to solve is that if you don't like manage your metadata well, you are going to hit the problem. So TableFlow proactively takes care of it so that user would never hit that problem. So that's how we like, there is nothing like, okay, there is more metadata, now we have to optimize it rather than doing it in a reactive way. Like TableFlow does it like automatically. Like if it's your metadata is of enough size, for example, you have like 100 manifest files in your table. TableFlow will next write will replace it with like a larger manifest with compacted. So this is like more like a proactive way.
Yeah, I've got a question. You mentioned that you use penny packing algorithm for compaction. So my understanding of that is within a partition you analyze the number of small data files, and if it crosses a threshold number, you trigger compaction. You said you see how query performance is affected by number of small data files crossing that threshold. I'm interested in knowing what sort of logic do we use to identify if the query performance is going to be affected by those number of data files.
Yeah, it's mainly based on the number of small files and the size of those files. So in an Iceberg table, like 128 MB to 1 GB is generally the sweet spot for the size, the Parquet file size. So we look at like smaller files if it's less than 128 MB, and if it's like, let's say 10 MB, that's even smaller, right? We consider that. Then we look at the number of such files. So there is a configuration. It's like internal configuration that we have tuned based on the workloads we have currently to trigger like if there is like enough small files based on the size and the number, we trigger the compaction to, let's say, write a new larger file. And there is like a target size as well, right? So if you take 100 small files and if the size becomes 5 GB, you split it into multiple large files so that you are within the sweet spot of like 128 to 512 GB.